Let's talk about when we have a sample where the gas in the sample is not just a single kind of gas. We have multiple different molecules of gas in the sample. Um, while it might seem like this is going to be terribly complicated, in truth it's actually not all that bad. So for example here in dry air, so just atmosphere, um, you're going to have about 78% nitrogen, 21% oxygen, about 1% argon, and less than a tenth of a percent carbon dioxide. So you have this mixture, and there are other things as well beyond those four, but these are the four main components. And if this was wet air, which is to say, any time in Oklahoma in the spring, summer, or good portions of the fall, when it's humid outside, water would be up here somewhere as well. But for dry air, these are the four main things. And it might seem like it would be complicated. You have multiple gases, it's going to be an issue, but in reality it's really not all that bad because, if you remember, most of the equations that we've used up to this point, we actually don't care what the gas is. We don't care if we're looking at nitrogen or if we're looking at oxygen. Gases, because they behave so similarly, we can just ignore the kind of gas that we are using in our sample. And so because of this, when we have mixtures of gases, we are actually going to, for most of the time anyway, treat them like it's actually just one gas. Because if all we care about is the total number of moles or the total pressure of the gas, we do not care if it's a mixture. Because all the gases are going to behave pretty much the same way. We can treat them as if they are all the same material, and we don't have to worry about having different numbers of moles of one gas versus another, or what we're going to see, it's called the partial pressure of different gases. We can ignore all that stuff if we're just caring about the total amount, the total pressure, the total number of moles. If we do care, if we are, for example, interested in the pressure that is due only to oxygen in dry air, what we're going to use to represent those individual pressures that are applied or produced by specific portions of the gas in a mixture, we're going to use what we call partial pressures. So when we have this mixture of gases, the pressure that is due to just one of those gases is what we call the partial pressure for that gas. So every gas in a mixture is going to have some portion of the total pressure that is due to that one molecule. And if you add all those together, so if you add all the individual partial pressures together, you will get the total pressure. And this is what we call Dalton's law. So Dalton's law of partial pressures essentially just says if you have a mixture of gases, if you add all the pressures together, you will get the total pressure. And that should make sense. Essentially, the sum of the parts is the same as the whole when it comes to pressures. We can take this a step further, though, because if we are interested in just the individual parts of the mixture, we can actually have an ideal gas law equation set up for each of those individual parts of the mixture. Now, when we're looking at the ideal gas law, there's actually only two things in the ideal gas law that are going to be dependent on the specific molecule that we're looking at. Because if we have a mixture of gases, they're all in the same container together. They're all going to, by necessity, have the same temperature and have the same volume. They have to. If it's a mixture of gases and they're all in the same container together, you can't have one gas occupying 1 liter and another gas occupying 1.5 liters. It just doesn't work that way. If you remember, gases expand to fill their containers. They're going to all have the same volume, and they're all going to have the same temperature as well, unless you just mixed them together and they were different temperatures a second ago. But if they've been in the mixture for any significant amount of time, they will have the same temperature, and they must have, under all circumstances, the same volume as well. and then R just being a constant, never changes. So the only thing that actually changes from one section or one part of the mixture to another is the pressure due to that one part and the number of moles of gas made up of that one part. So if we take Dalton's law and kind of combine it with this idea of having ideal gas equations for each one of those different parts, we can essentially have an ideal gas law for each individual section of the mixture, and then if we need to solve those for the pressure, we can plug those pressures back in down here into Dalton's law. But the main thing here is that we can either treat all the gases as one, essentially, if all we care about is the total pressure and the total number of moles, or if we need to, we can split them apart. It just depends on what we're interested in. It depends on what we're looking for. So in this question, for example, it asks, it says a 1 liter mixture of helium, neon, and argon has a total pressure of 662 millimeters of mercury at 298 Kelvin. If the partial pressure of helium is 341 and the partial pressure of neon is 112, what mass of argon is present in the mixture? So I'd like to encourage you to pause the video here and see if you can figure out a way to work this out yourself, and then come back in just a second and we'll work it out together. Alright, so we have a mixture of 3 gases. We have helium, we have neon, and we have argon. So we're given information about the helium and the neon, and we're asked to find the mass of the argon. Now it might seem kind of odd, like we're just throwing mass in here all of a sudden. We don't have mass in the ideal gas law. We didn't have mass in the in Dalton's law. But if you think back to the ideal gas law, mass is not in the equation, but the number of moles is. And if we can find the number of moles, since we know that what we're looking at is argon, we can use the number of moles to find the mass. So what we're really trying to find here is going to be kind of a two-step process. Figure out how many moles of argon we have, and then figure out what mass of argon that would be. Now, to figure out the number of moles of argon, we're going to have to work with Dalton's law, because we have a mixture and we are concerned with just one part of the mixture. We need to find the pressure, volume, and temperature of argon in this mixture. This is always just a constant, so we always know that. And most of the rest of this is just given to us. So the temperature, which is one thing we need to find, is just given to us in the problem. It's 298 K, so we know that. The volume also is just given to us. We're just told that it's 1 liter, so that's good. We know what that is. What we don't know is the pressure, but we are told the total pressure, and we're given the pressure of the other 2 gases. So what we're going to do is we're going to say 662 millimeters of mercury is equal to the pressure of argon, which we don't know yet, plus the pressure of helium, which is 341, plus the pressure of neon, which is 112. So the algebra here is pretty simple. We're just going to add these 2 together and then subtract that from both sides. So if I do that, let's see, 662 minus 341 and 112, that leaves me with the pressure of argon. The partial pressure of argon is 209 millimeters of mercury. Now you might have noticed that up to this point if we've had a question where the units were not in the right, the correct unit, we didn't have the correct unit for something, that I usually would go ahead and do that conversion at the beginning. I did not do that here, mainly because I would rather convert one thing than three. So if you notice here, all three of these are in the wrong unit. We're going to need those in atmospheres for our pressure unit. But if I convert this now, then yes, I won't have to convert this. I'll already have it in atmospheres. But I'll have to do the conversion for all three of these to get all three of them in atmospheres. But if I do the algebra first here, now I would just have to convert the one number. And so it would work either way. It's just slightly easier to save the converting till now. So we have 209 millimeters of mercury. And if you remember, 760 milliliters of mercury is the same as 1 atmosphere. So if I go ahead and do that math, I have 0.275 atmospheres is my pressure. All right, so now I have my pressure, my volume, and my temperature, and again I always have that constant. So I'm going to go ahead and solve for N. So if I divide both sides by RT, that will give me PV over RT is equal to N. So if I go ahead and plug in all of my known values here, I have 0.275 atmospheres of argon. The volume is 1 liter. R is 0.08206, and I'm just going to go ahead and leave the units off just like before, just because I'm going to run out of space here. But you can just trust me that the units will work out there. The temperature is, let's see, what was it, 298. And the units there were liter atmospheres per mole K. And so if I do the math, 0.275 divided by 0.08206 divided by 298. The number of moles of argon that I have is 0.011, let's see, 2 moles. And argon, got to grab my periodic table here. I do not remember what the molar mass of argon is off the top of my head. It is about 39.95. Okay, so if I have this many moles, and the molar mass tells me that for every 1 mole I have 39.95 grams. If I do that math, I'm going to have essentially 0.45 moles, or sorry, not moles, grams. All right. I think we'll call it there for this video. We'll talk about collecting gases briefly in the next one. So I will see you all in the next video.